Swayam Prabha. Digital India. Educated India.
In the last lecture, we saw that the distinction of science is untenable, or distinction between the internal world of science and the external world of science is untenable. We also have seen that the science as a force of production is related to technology. To recall the relationship between society on the one hand and science and technology on the other, I would like to show the picture again, which I showed in my very first lecture. This picture shows that societies prior to technology or science, human society is a prerequisite for producing any technology or any science. In that sense, society, as I said, provides human resources and personnel, cultural resources, language, beliefs, values, and meanings, physical resources like funds, space, and infrastructure, and society also accords legitimacy to scientific and technological activity. Now, why I am showing technology first, from society to technology first, is that technology predates modern science. I said even before modern science became an alternative system of knowledge in the 16th century Europe, alternative theological knowledge, the technologies were used. Several kinds of technologies were used. People were using horse-drawn carts. People were using techniques to lift water from groundwater. Persian wheel is an example. And people were using bows and arrows. People were using iron plows to till the land, and so on. All this has been based on their experience over centuries or several years. As I said in the last class, that the people also selected some edible plants, edible seed, and then they started cultivating them on the field and started preserving them on the field or in situ preservation. Now, in the sense, these were technologies. These were done on the basis of their empirical experience, and for a long time, they did not know the, for example, laws that govern the movement of an arrow when it's released from the bow. And similarly, they did not know the laws of genetics or principles of genetics that govern the acquisition of hereditary characters among in the plants. So they were all these technologies working, but only after 16th century, scientific knowledge became available, and they could produce theories to account for this technological applications. So that's why if you look at the kind of relationship between science and technology, you will see that over time, there have been changes in the conceptualization. One, earlier conventional conceptualization was that science is the act of knowing and technology is the act of doing. In the sense, scientists devote their time, energy to understand nature, understand laws of nature, and try to formulate the theories on the basis of what they observe. And these theories and scientific knowledge used by technologies for producing artifacts like products, processes. In that sense, science is placed on a higher plane compared to technology. Technology was at a lower plane because technology only involved application of science, which is more or like mopping up operations. And that's why sometimes there is always a conflict whenever, for example, there is a position of a director of a an institute falls vacant which is engaged in research on or development of certain products like certain things like atomic energy, the question is who should become director? An engineer should become, or a scientist should become a director. And this happened in our country, India, several times. So this is the hierarchical model of the relationship between science and technology. Similarly, there is a symbiotic model which treats science and technology as parallel structures or parallel cultures. The third is technoscience, which is basically much more than science and technology, which includes several associations, networks that are involved in doing research and producing products. And in that sense, they are interpenetrating systems of knowledge and the interface with society in production process. As I said, hierarchical relations, science is the act of knowing, and that includes producing abstract knowledge in the form of theories, models, and about natural phenomena. The theories provide explanations which can be used in developing techniques and artifacts, as I just now mentioned. For example, Newton's laws of motion are applied in designing automobile engines. Knowledge of material science is used in making artifacts. Here, technology is seen more as a mopping up operation or merely application of science, and hence not an inventive activity. This is, of course, contested now. Technology also can be seen as a knowledge that will come to later on. That's why I mentioned there's always a problem, tension in terms of who should occupy a position of a directorship of an institute engaged in production of atomic energy, whether it's an engineer or a scientist. The symbiotic model was developed by Derek Desola Price, who contributed a significant amount of, who made significant contributions to understand science as a social science in society. And he argues that science and technology are parallel systems or parallel cultures. The culture of science is papyrocentric. It means scientists want to publish the research as quickly as possible so that they can stake their claim for recognition. That is, no scientist wants to keep his results unpublished. If the results make sense, if the results appear reasonable, they would like to communicate to a journal for publication so that they get recognition. As I said, in science, if you do not publish as quickly as possible, somebody else might publish it, because at any given point in time, there are more than one group which is working on a particular set of problems. So that's why there is a high degree of competition in science to publish. Second, whereas culture of technology is secrecy, it's also called papyrophobic. According to Desola Price, technologists are papyrophobic. They do not publish. They maintain secrecy. Technologists do not publish as much as scientists do. As the technologist wants to produce an artifact that can be sold in the market. He maintains secrecy until the product is produced, at least in the form of a prototype, so that no one copies it. Today, the product and the process of producing the product are protected by patent laws or patents. See, in the case of agriculture also, similar kind of thing happens. The plant breeders who are supposed to develop new varieties, they do not publish much compared to people who work in the area of genetics, who work in the area of other areas of basic science. Plant breeding is a kind of a field-oriented activity where the plant breeders produce new varieties. Okay, so that's why the plant breeders do not publish much, because until a variety is proved, until a variety is tested in several locations, it is not released to public, nor is it published. Then science and technology have symbiotic relations, and they may interact with each other by producing or by providing knowledge resources to each other in their efforts. That is, symbiosis means one needs the other. One really somehow requires the presence of the other for the growth. Discipline Price says that science and technology are a pair of dancers who dance according to the tunes of each other rather than an external tune. In the sense, he says that the symbiosis between science and technology results in newer kind of branches of knowledge, newer products, and that's how they take cues from one another and start working to produce newer ideas and newer products. In the sense, technology also contributes to the growth of science. For example, invention of tunneling microscope created a new field of nanoscience that enabled scientists to understand materials at nano level, between 1 and 100 nanometers in size. Materials at nano level exhibit different properties. For example, gold at nano level is not yellow in color. That's why today nanotechnology holds a lot of promise for various applications in agriculture, for sustained release of pesticides and micronutrients by using nanotechnology, nanotubes, and in the case of paints and several fields, the nanotechnology is being used to develop products. And we are also familiar with science contributing to technology. Molecular biology facilitated the development of biotechnology or growth of biotechnology. Biotechnology, as said, involves several techniques. Of course, the most important the techniques are genomics-based techniques today, that is genetic engineering, and in the case of plants, it's genetic engineering, which developed out of the advances in molecular biology. Molecular biology enabled scientists to understand life processes at molecular level, and which also created possibilities of intervention at molecular level. Earlier, agriculturists were working with an understanding of phenotypes. That is, they understood the properties of particular varieties of crop by looking at the phenotypic characteristics which can be seen by naked eye. And today we are looking at the life processes at molecular level or genotypic level, which also helps us in intervening at molecular level. Technology as knowledge. Leighton in 1974 observed that technology is knowledge. The terms science and technology are historically produced. Sometimes science and technology mean the same thing. For example, nanoscience and nanotechnology are indistinguishable today. Even in the past, what the difference between science and technology were not made in a very strict sense. And as I said, technology also has a knowledge component. Now let's come back to this, how pervasive is science and technology in our lives. Today we cannot talk of society without talking about science and technology, nor can we talk about science and technology without talking about society. They are pervasive in all domains of our lives, whether it's economic life, it's social life, cultural life, or in trying to do certain things like traveling or transport. We also depend quite a lot on mechanized transport system like buses, railways, and so on. So it's so pervasive that we cannot think of our life without some kind of science and technology gadgets, technological gadget associated with our life, or some kind of understanding of our nature by using our scientific concepts. We are going to look at the technological developments relating to important domains of human life and discuss the consequences. In an earlier lecture, I mentioned about the different and interrelated elements of technology, the artifact, the knowledge underlying the construction of the artifact, and social organization that is required to implement the technology. And I also drew your attention to the idea, the concept of design. The design of technology includes at least two aspects. One is the functional aspects. It means that a particular product made should serve the function for which it was made. For example, if a refrigerator is made, it must keep the substances at a particular temperature. And the next thing is aesthetic part, that is the color, size, shape of the artifact which appeals to our eyes. And I also mentioned that recent literature suggests that the design incorporates the values, ideologies of the designers. There are examples. We're going to discuss those examples today. See, let us see the earlier theories talked about certain kind of technological determinism. Technological determinism means that technology shapes society as an independent force from outside. Given a technology, there would be a particular kind of society. That is, the technology, as if it is an outside element, is going to shape the society without reference to the efforts of people to develop techniques, better techniques. So technologists apply scientific knowledge to work out practical implications of new scientific theories and discoveries, and they produce products or processes. And I quote from McKenzie and Wackman, who published an anthology of articles on the social shaping of technology. And I quote, "Scientists discover, technologists follow the logic of those discoveries in turning them into new techniques and new devices. And these techniques and devices are then introduced into the society and have effect, often unprecedented effects." I close the quotation. In other words, technology is autonomous and outside, and it causes social change in the society. For example, a famous statement attributed to Marx is, "Watermill gives you a feudal society." Of recent developments, if you look at the recent developments, we can now say a microchip gives you an information society. This is kind of a technological determinism, which of course have serious. This view of technological determinism as a theory has a serious limitations, because it does not recognize the needs of people, which really sometimes bring about innovations. It does not recognize the efforts of people who would like to develop new techniques, who do develop new techniques. So it is seen as if technology is independent of society. It is it's only going to be introduced for in the society, and the society has to adapt itself to the new technology. The example given earlier, that microchip creates an information society. However, this is a simplistic notion because A, the characteristics of a society play a major part in deciding which technologies are adopted. It is not that societies blindly accept technologies. Societies blindly use technologies without evaluating them in terms of whether they are useful or not, whether they are affordable or not, whether it really is compatible with their culture, compatible with their meaning systems, and so on. Just now also, in the earlier lecture, I mentioned that the US adopted genetic engineering technology to modify food crops. It's accepted. European countries resisted the adoption of genetic modification of food, and in India also, we do not have any GM food today. In the sense, we see the characteristics of society play a part in either accepting or rejecting a particular technology, in the sense that different cultures, different social structures look at technology differently. The second limitation of technological determinism is that some same technology may have different effects in different situations. This is an important observation made by McKenzie and Wackman. And for example, how does this happen? Same technology may have different effects in different situations. In the sense, a given technology may have one kind of effect in American society, another kind of effect in other European society, and yet another kind of effect on African countries. There are several examples to substantiate this. And for example, see what is the impact of introduction of automobile in different societies, right? Now, the effect can vary across countries. See, the innovation, The effect of automobile coming into market, people buying it in the US led to what is called suburbanization. People who did not want to crowd in the city, they went out of the city because the car could bring them to work from the suburbs. In some other countries, perhaps it may not happen. People still would like to crowd around the city because that's where their work sites are located and they would like to continue to live there. So, these different effects can be seen in effects of technology can be seen in different situations. Same technology will have different kinds of effect in different situations. Now let us see what factors shape. Once you say that technological determinism is not several limitations in explaining how technology is developed, then we should look at what factors shape technology and what are the consequences of technology. McKinsey and Wackman, about whom I just now mentioned, list some factors that shape technology. And these technologies, people have talked about these factors earlier also. Let me list these factors. One, the factors that shape technology are economic factors. Generally, the economic considerations are efficiency and productivity. Efficiency means we would like to produce more by using less, or we would like to produce more in less time. Productivity means it can be related to a per unit of labor or per unit of land and per unit of capital that is invested. So that we would like to produce more and more by using our labor and less labor and more productivity. Similarly, we would like to produce more per hectare of land that we cultivate or per acre of land that we cultivate. That is, if I get, let's suppose hypothetically, 20 bags of wheat from 1 acre, I would like to see that it goes up to 40 bags. That's what we mean by productivity per unit of land. Then social factors that shape technologies or institutions, social institutions, which also sometimes lead to development of technologies. And political institutions can also sort of shape technologies. For example, those examples we're going to see now, and cultural domain of our life also can lead to innovations or development of new technologies. Creative pursuits like science and technology, creative arts like dance, music, sculpture, and so on. Several new things can really be. Culture also was an important factor in the development of technology. And systems of meaning. Culture includes systems of meaning. And third thing is existing knowledge, that is existing scientific knowledge and existing technological knowledge. Now, what are the consequences of technology? For example, we're going to see this in the next few lectures. The consequences are also economic consequences. That is, if your economy becomes more efficient, if you are able to produce more per acre of land, if you are able to produce more per unit of labor spent, if you are able to produce more per unit of capital you invested, then you generate wealth in the country, wealth in the society. That is, you produce more food, surplus food, sell the food, you produce more industrial products, sell them and generate wealth. The question is, when you generate wealth, how does this wealth get distributed across the society? That is, you can generate a lot of wealth, but there can be a lot of poverty in the country, poverty in the society. How does one account for this? How does one eliminate poverty? And how does one redistribute the wealth? The redistribution of wealth is a political question. It is a political question which has to be decided by policymakers, decided by the parliament of the country or legislature of a particular state. See, for example, the public distribution system is an example of redistribution of our wealth in the wealth we produce in agriculture in the form of agricultural crops. That is, we try to ensure redistributive justice by making food available to poor people at an affordable price. So what are the social consequences or changes in the institution? For example, the institution of family is no longer the same as it was 50 years ago. The interrelations or interpersonal relations among the members of the family have undergone change because of some technological innovations that came into the household. For example, household gadgets perhaps contribute to change in the relations between spouses and relations between parents and children. And as I said, political consequences of technological development is with respect to distribution of power. And I said, how does power, as a result of technological developments, how does power get distributed? Who becomes more powerful, right? So this is where we talk of highly centralized technological systems or decentralized technological systems, where the power distribution in the two cases is very, very different. In a highly centralized technological system, power is concentrated in a few hands. In a decentralized technological systems, power is distributed across the different sections of the society. Then I said the impact of technology is also cultural, in the sense the technological gadgets change our attitudes to life, change our attitude, change our meanings, and we try to make use of technological gadgets that are produced. In the sense, here this is where advertisements plays an important role. In the sense, if you watch TV today, the advertisement says, our product is going to make you different. The old products, the old way of doing things that you are practicing are inferior to what our product offers. If you buy our product, you are a better person. You'll have better kind of status. So that is how the attitude towards new technologies are changed through advertisements. The attitudes are changed, and there is always a ranking involved in between older ways of doing things and newer ways of doing things. And the advertisements say the new things, new products, new processes are superior to the old products, old processes. Then the next important impact that we're going to observe is environmental impact. What does technology do to the environment? If you see that over the last 200 years, I mentioned in earlier lectures also, that people have been exploiting nature without any kind of a control. This is uncontrolled or unbridled exploitation of nature, created several environmental problems. For example, our industry creates pollution, air pollution, water pollution, soil pollution. Our automobiles create pollution. And how does one really see that the design of automobiles are changed in such a way that they do not emit poisonous gases or emit toxic gases? Similarly, we must design a system for treating industrial effluents so that they do not become toxic when they're released into air, water, and soil. We'll examine these issues later on. We're going to discuss several case studies about these, both the generation of technology and impact of technology. One statement I would like to make here is, technology is not a neutral phenomenon, it is not a neutral force. Conventionally, it is held that technology is neutral, but its effects depends on who uses it and how is it used. This is a very, very simplistic statement in the sense that earlier people used to say, okay, technology can give results, same results everywhere, but it depends on how it's used, who is using it, who is controlling it. As technology is shaped by various forces and it operates in a social, cultural, economic and political context, it cannot be neutral. It is not a neutral force. It always creates conflicts among people. It always creates some kind of tensions in the society. And because various interests are involved in shaping technology. Several examples are there. We would like to build dams across rivers, and this creates a lot of tension between those who want to build the dams and those who really are going to experience the impact of these dams in terms of losing land, in terms of losing their habitation, in terms of displacement and so on. So similarly, several cases of conflicts can be seen when a particular technology is being implemented. One familiar example I would like to give here is, look at our cities today. All the major cities have a lot of automobiles on the road. You have motorbikes, you have cars, you have other kinds of vehicles. As a result, pedestrian has no place in the city. Our cities are turning out to be anti-pedestrian cities, where it is impossible for a pedestrian to cross the road. And so this is what sets up some kind of tension, new technologies, unless they are regulated, unless they are seen that they take care of the interests of the others. I mentioned just now, a few minutes ago, that the design of technology incorporates the following features. One is functional aspects. Second is aesthetic aspects. I mentioned just now, functional aspect means that a gadget designed should perform the function for which it was designed. A refrigerator must keep the substances at a particular temperature. For example, a motor car should be able to run on the road. And these are functional aspects. As aesthetic aspects refer to, for example, the size of the artifact, color of the artifact, the kind of appeal that it has for the customers. So these aesthetic aspects are also an important part of the technological design. But there are more serious kind of elements are involved in design. This refers to the values and ideologies of the designers that go into the design of this particular technology. It means technological design also incorporate who will be included and who will be excluded. It also incorporates inclusion and exclusion. It also incorporates some power relations. So the designers will put into the design what they think is good for the society, what they think the technology should do, and who should have access to this kind of technologies. So this is the designers' values, ideologies, and we'll see how these ideologies function when a technology is developed, when a technology is technological artifacts are built and used, put into practice. What shapes technology? As I just now mentioned, several factors that shape technology. One popular understanding is that scientific knowledge is used to work out practical implications. I said science and technology also influence technological development. Production of one popular understanding, let me repeat, one popular understanding is that scientific knowledge is used to work out practical implications, that is production of techniques and devices. The technologist is independent and produces new artifacts, and they are released into the market. It means that technology is an independent force and it will shape the society. In other words, the society gets adapted to the new technology rather than the other way around. The view that science leads to technology and technology creates some social effects is a simplistic understanding today. We have seen earlier in our earlier lectures that science is influenced profoundly by the society in which it is practiced. We will see that technologies are socio-technical systems in which technical, social, and economic aspects are intertwined. Does economics shape technology? I just now mentioned the economic factors, basically the criteria of efficiency and productivity, shape technology. And the idea of efficiency and productivity are context specific, right? Then the questions that one has to raise are as follows. Efficiency to what end? Why are you doing it more efficiently? Who is it going to serve? Second, and productivity for whom? If you produce, let's say, if you increase productivity of 1 acre of land from 20 bags of wheat to 40 bags or more, who is it going to serve? So how that this kind of productivity will be useful for the society? How increases in productivity will be useful to society? Answers to these questions boil down to the social. For example, the cost of a particular commodity. Before that, for example, the notions of efficiency and productivity are context specific. What does efficiency do to American society? What does efficiency do to societies in Europe? And what does it do to societies, developing countries or emerging economies is very different. Next, for example, the cost of a particular commodity varies across societies, contexts. The same product may be sold at different prices in different contexts. In other words, the economic criteria are ultimately related to the social context. For example, the pricing of a commodity, the future pricing of a commodity, and how is it going to be priced and at what level is it going to be priced so that it can be sold in different markets. That is, in the sense, ultimately the economic criteria boil down to context specific or economic criteria tend to be dependent on the context. The economic shaping is in fact social shaping of technology. In the sense, ultimately, who wants to produce more, who wants to produce efficiently, who wants to produce more, or who wants to increase productivity. It means that those who have means of production, those who own the means of production, are the ones who would like to introduce new techniques to produce efficiently, new techniques to produce more, or new techniques to increase productivity of land or labor or capital. I would like to present one paper by Langdon Winner, who wrote an interesting article, Do Artifacts Have Politics? I said in the beginning, politics also shape technologies, and ultimately they also have political implications. Let us see what Winner does. Winner argues technical systems of various kinds are deeply interwoven in the conditions of modern politics. That is, today technical systems are closely linked to political systems or modern politics. The physical arrangements of industrial production, warfare, communications and the like are fundamentally changed, have fundamentally changed the exercise of power and the experience of the citizenship. In the sense, today several things are arranged according to certain pre-planned kind of strategies, particular way of organizing warfare, particular way of organizing industrial production. All these are done before the production takes place. For example, the arrangement of machinery in a particular industrial unit or industrial enterprise is done according to certain criteria. One of them is important criteria is how to control the machinery, what kind of arrangement will enhance the control over machinery by those who supervise the production, by those who really control production process, and by those who actually own the enterprise. He says that one popular view is that artifacts have political qualities. What matters is not technology itself, but the social or economic system in which it is embedded. This is a notion which a lot of people say. There's nothing wrong with technology, but it depends on who is using this technology and how is it being used. And we keep hearing this on several occasions, in several situations. The second view which Winner vehemently puts forth is that artifacts have political properties rather than political qualities. He subscribes to the second view and substantiates it. That is, he says artifacts have political properties. He defines what he means by politics. One, he says politics refers to arrangements of power and authority in human associations, as well as the activities which take place within those arrangements. By technology, he means all of modern practical artifice, and he prefers to use term technologies rather than technology. He gives the example of the overpasses designed by Robert Moses over the parkways of Long Island, New York in the early 20th century. He presents this case study to indicate how the political values, ideologies of designers can influence the products. Robert Moses was a builder of roads, parks and bridges and other public works during 1920s to 1970s in New York. He designed the overpasses and this height looked very odd for some people. The 9 feet tall overpass, that is, or only allowed cars to move through that, whereas buses could not move through the overpasses because buses were 12 feet tall. The height of buses were 12 feet. That is, you understand that the height of the underpass is 9 feet, which does not allow buses to pass through these. Why did he design 9 feet tall underpasses rather than 12 feet tall underpasses? The reason why Robert Moses designed the 9 feet tall overpasses was his social class bias and racial prejudice. According to him, automobile owning white upper class and comfortable middle classes would be free to use the parkways for recreation and commuting. Poor people and blacks who normally use public transport facilities were kept off these roads, off these overpasses, as the 12 feet tall buses would not go through the overpasses. In other words, the design incorporated Robert Moses' ideology and values. Robert Moses was a highly successful contractor. He interacted with city mayors, governors, presidents, but he could implement the design that clearly defined access to racial minorities and poor people. Winner gives several examples of designs that had political ideologies built into them. It is not the efficiency as we normally believe that guides the design of technology in some cases, but several other motives, such as designs compromise on efficiency and demonstrate political domination over others. So all the time we can't say that efficiency is the criteria that is employed to introduce new techniques. Sometimes a technique that is introduced, a technology that is introduced may not be efficient, but it may enhance the control or domination over workers in a particular enterprise or particular industry. So this has been shown in several cases, and he gives all the examples. You can go through this article. Such designs compromise on efficiency and demonstrate political domination over others. Sometimes some machinery are used even though the machinery is not efficient, I just now mentioned. It is done in order to remove workers, to reduce the influence of trade unions. So this is what you see, some machinery, although is not efficient, your motive is not efficiency, but your motive is to reduce the number of workers and remove the influence of trade unions from the industry. In other words, technologies can be used to enhance power, authority and privileges of a few over others. For example, you have seen in India several controversies, for example, over dams, small or big, heights of dams, what height should be the dam, at what height the dam should be built. And all these decisions regarding the introduction of mechanical implements, all these reflect political debates and decisions. For example, the whole debate over Narmada project is an example. A lot of people started questioning the design of the dam because it was going to affect the people who live downstream, and people's loss of habitation and loss of their resources, community resources. So always there is a tension, this kind of the technologies do not operate in as I said, always in a situation of conflicts, in a situation of tensions. And how does one arrive at consensus? It's a big question. And Langdon Winner also says that there are certain artifacts which are inherently political in nature. There's no other property except political property of these technologies. Langdon Winner points out that adoption of technological system or a technical system brings with it elements of political power distribution, centralized or decentralized, egalitarian or inegalitarian, repressive or liberating. He argues that certain technologies are so designed that they do not allow flexibility, and choosing them is to choose one particular form of political life. He gives the example of the atom bomb. Atom bomb is inherently political artifact. As long as it exists, its lethal properties demand that it be controlled by a centralized, rigidly hierarchical chain of command, close to all the influences that might make its working unpredictable. This is in continuation of my lecture which I delivered in the morning. Let me begin this lecture. Today, all of us, we receive electricity at our doorstep. Our rooms are lighted with electric bulbs. Wherever you are, whether in kitchen or living room or reading room, rooms are lighted up. The electric bulbs are connected to your house. Every room has an electric bulb. And we all are really enjoying the facility that was created in the 19th century. Now we should see how the whole electrical supply system came into existence and how the electric bulb was invented and it was connected to electrical system and electricity, how electricity provided energy for the bulb to glow. And we all take these things for granted. At the switch of a button, we get our lights, we get our fans switched on, and we get our air conditioner switched on. But there's a big story behind this, and one should really understand how it all came about and what are the various dimensions of this kind of a major invention that was made in the 19th century, which really has really created so many possibilities of comfort for all of us today. Now, this study is about Edison and his electric bulb. We all know Edison was the inventor of electric bulb. It's not enough to invent electric bulb. You also have to see how it's going to be connected to electricity, how it's going to be delivered to every household so that the electric light can be used by households. So this is a big challenge. I think it is Thomas Edison who thought of this idea of inventing this electric bulb and also making sure that this electric bulb was used by every household in the country, in the US. This was his great idea, great concept, and all inventors come up with this kind of simple but profound questions. How do you provide lighting to your house, to the households? How do you provide better lighting to the houses which are using gas burners? I think these are the questions with which Edison started his work. And this was documented by Thomas Hughes in his study of Edison and his electric bulb. See, the Hughes study of Thomas Edison's invention of electric bulb demonstrates that the journey from invention to innovation involves scientific, technological, organizational, economic, legal and political dimensions. Not only invented the electric bulb, but also invented an organizational framework that was required to move from invention to innovation. We know that invention is the concept of that it's possible to produce this particular product, and it is with that idea of the possibility of converting a concept into a product, you start working and putting in place several things to reach that goal. Innovation is something which is a novel product or a process that has been introduced into the market a society by using either existing knowledge or by making use of the new knowledge that has been generated in various fields. That is, innovation requires several kinds of inputs from several disciplines to see that the product is introduced into the market. So, as I said, Edison not only invented the electric bulb but also invented an organizational framework that was required to move from invention to innovation. In other words, activities covered a broad spectrum from invention to innovation. He approached the problem solving systematically, and his inventive method synthesized the technological, economic, scientific, political and legal dimensions of the innovation process. So basically he was organizing himself and his team for the innovation. Edison was an inventor entrepreneur. He organized an entire system that encompassed, as I said, scientific, technological, organizational, legal, economic and political elements, including administrative elements. His genius lay in selecting people with appropriate skills for the project, and these members of the team also shared his vision, shared the vision of Edison. That's only then the team could work in an integrated way to achieve the goal. So what happened in the 19th century, late 19th century? Edison moved to Menlo Park, an area where he established a research laboratory. The Menlo Park was located in a rural setting and quite away from city. He thought this will not distract his team members. The city glamour will not distract these team members, and they would focus on the work. Of course, it does not mean he made them work under duress. They all enjoyed working. It seems sometimes they worked for 24 hours a day, and then at the end of the 24 hours they celebrated. So, so that is the spirit with which he really nurtured the team, mentored the team to see that his goal is achieved. That is the great leadership quality of persons who who has a vision, and they work towards that vision by taking people along in a spirit of democratic spirit, and to see that they also share the vision and they don't see the work as a burden, but they work with passion. Since he took the decision, his research was far more extended and sweeping. He was ready to preside over the introduction onto the market of a complete system of technology synthesizing components of his own invention. As I said, after moving to Menlo Park in 1876, he decided to introduce a system of electric lighting in 1878. So he took 2 years, he organized the lab and started working towards developing this electric light and the entire system of supply of electricity to the households. As an inventor entrepreneur, Edison coordinated a team of electricians, mechanics and scientists and cooperated with associates concerned about the financial, political and business problems affecting the technological system. In the sense that we see that the process of innovation is not merely converting an invention or proof of concept into product. It also involves handling several interrelated dimensions like financial dimension, political dimension, business problems affecting the technological system. In a sense, he created a system which is socio-technical system. He created a socio-technical system in which both the technology and the social, cultural, political, economic, legal elements are brought together, and this is what we mean by a socio-technical system. Technologies are not merely artifacts, they are socio-technical systems in the sense that there are several elements related to the technology, as I mentioned in my earlier lectures. It's not merely an artifact, it also involves knowledge that is required to construct the artifact, and of course a social organization that is needed to implement the artifact or the product. Here in this case, the invention of electric bulb is not enough, but it has to be seen that it is used by households by making sure that electricity is supplied and the bulbs are connected to a source of electricity. Now, this is a broad spectrum of activities for which he needed different skills, different people with commitment who could work with him, and that's how he recruited very, very talented persons to work with him. Another characteristic of inventor entrepreneur is his vision. Edison told the reporters of the newspaper, the New York Sun, on October 20th, 1878, of his plans for underground distribution in mains from centrally located generators in the great cities, predicted that his electric light would be brought to private houses and simply substituted for the gas burners at a lower cost, and confidently asserted that his station would furnish light to all households within a radius of half a mile. In the sense, that is the vision. So, an inventor, entrepreneur does not only have an idea or a concept, but he also would work towards realization of this concept or translation of this concept into a product, and also put in place a system that is required, that the social organization that is required, where this artifact would be used by every household, right? The vision is based on the fact that he had the concept and he systematically went about translating the concept into a product. So this is what gave him confidence that he could achieve this, and we could see that the product would come out of this concept. He did a great thing like matching skills with tasks. As I said, invention, the movement journey from invention to innovation involved several related tasks, and to ensure that the tasks are performed in consonance with the project, in consonance with the goal of the project, he had the following people who shared Edison's vision and worked for realizing the goal that Edison set for himself and his team. To perform scientific tasks like scientific literature search and also trying to find out important relevant scientific information for the project, he appointed Francis Upton, who did extensive survey of what is available in scientific literature that is relevant for the project. Then lamp filament investigation, Francis Gell. See, it's not, the bulb has to have a filament which we should not really burn out as soon as electricity is supplied to it. It should have resistance, and for identifying the material which could provide the resistance, the investigations were carried out by Francis Gell. Then for experimental techniques, he had another master craftsman who was Charles Batchelor. He was a master craftsman, he is very familiar with several experimental techniques, and the other thing, legal matters, political and financial matters, were seen by Grasvenover Lowry, who was an advocate, who was an attorney, who was very well informed about the legal procedures and kind of policy issues, and of course financial matters that are very much relevant for the innovation to succeed. Mobilizing varied talents explains the encompassing character of Edison's concept of the system. It shows that Edison was not a tinkerer or an opportunist who saw short-term gains. He waited patiently like a hedgehog and stayed focused on one goal until the goal was reached. Hedgehogs are those who relate everything to one central vision, one system, less or more coherent or articulate. On the other hand, foxes in contrast may pursue ends often unrelated and even contradictory. Edison was a hedgehog. See, this kind of a comparison with foxes and hedgehogs is generally done to show that people who concentrate on one particular goal, people who look for, wait for one big thing to happen, or hedgehogs, whereas foxes, they move here and there, goalless. Sometimes they have contradictory goals and unrelated goals, and ultimately they don't achieve much. Now, I think that is the hallmark of an inventor, entrepreneur, who stays focused on the work until he or she achieves his or her goals. And why did we do this? Why did we read this, or why did we look at Edison's work? It's basically to say that technologies are not merely artifacts; they are socio-technical systems, and there must be, if somebody is inventing a particular product, he also must think of inventing a framework within which it can be implemented, within which it can be used by people. And this is what calls for vision, and of course a kind of a perseverance with which one should work towards the goal. Achieving the goal. In September 1822, the Pearl Street system began to supply light for the Wall Street district in the US. With the opening up of Pearl Street Station of the Edison Electric Illuminating Company, the age of central station incandescent lighting had begun. The modern age of public electric supply opened. So this is what I was referring to when I began introducing Edison's work, that today we take a lot of things for granted. We take things simply have happened in the past. It is not the case. This was deliberately created by a person with passion, person with vision, a person who wanted to put in place a new system, put in place a new way of organizing things. And that is the genius that we should salute Edison. That's the genius. Edison was a genius. We all must salute him for making life comfortable for all of us today. Thank you very much.